Hello everyone, I'm Cherukuri. I work in the quant research group at Bloomberg. In my talk today, we look at how deep learning methods can be used for building fast option prices. I'll start with a very brief overview of options, and then we look at classical quantitative finance techniques used for option pricing. We'll then see how deep learning methods can be used to expedite the pricing of options. And along the way, I'll also show you demos of nice interactive applications which can help us better understand these models. So, what are options? An option is a derivative contract which gives the buyer the right to buy the stock if it's a call option, or the right to sell the stock if it's a put option at a specific price. It's called the strike price, and on or before a specific maturity date. So the strike and maturity are the part of the option contract. The nice thing about these options, unlike stocks, is there is no obligation to execute on the contract. So at expiry, if you don't find it favorable, you just walk out of the contract. And call options help us express a bullish view on the stock. So we buy the stock at the option at a strike which is lower than the current stock price, and then you can hope that if the spot price goes up, you make money. And the payoff is a nonlinear function. It's the positive part of S minus K. So that's why options are nonlinear instruments. And similarly for the put option, we express a bearish view. So if the stock goes down, we make money. These options are not free because of this optionality. So there is a price, it's called the premium. So we need to pay the premium upfront if you want to enter the contract. And that premium is called the price of the option. So here we have the PNL diagrams. As you can see, for the call, the payoff is nonlinear. And the PNL is just, you take the payoff and subtract the price of the option. And similarly for the put option, you can see that the payoff is like this. So if the stock goes down, you tend to make money. We can also have different exercise styles for options. European options can be exercised only on the maturity date, whereas American options can be exercised any time before the maturity. So because of that, the pricing becomes complex for American options. You need to use some numerical methods like PDE solvers or dynamic programming to price American options. The price of a European option, on the other hand, is very easy to compute in models like Black-Scholes. It's almost, it's a closed form solution. European options are mainly used for index options, like options on S&P 500 is European, whereas most of the single name stock options are American. So therefore, we have higher volumes for American options compared to European. And because of this exercise style, American options tend to be more expensive because you have the option to exercise any time before the maturity. Let's now look at some what are the inputs which are required for option pricing. The most important is obviously the spot price. The spot price is the price of the underlying asset. So you can have options on stocks, then it's a stock price. If you have options on currency, exchange rates, then it's the FX rate, commodity prices, whatever, right? And then we need the interest rates and dividend yield or convenience yield if you're using commodity options. The first three are observable in the market, right? You can observe all these prices in the market. But volatility is a very important parameter, but unfortunately we cannot observe volatility or the risk of the underlying asset. And the only way to get this feature is to estimate it from the price series. And maturity and strike price are the parameters of the contract. So these are all the inputs to the pricing model. And not only prices, we can also compute the sensitivities of the prices with respect to all the inputs. These sensitivities are very important for risk management. For example, delta is the sensitivity of the call price with respect to the underlying asset. And delta is very important for hedging. to maintain a hedge as the time progresses towards the maturity. Gamma is the sensitivity of the delta with respect to the spot, or it's the second derivative of the call price with respect to the spot price. Theta is the time decay. As the option approaches maturity, the price goes down, and theta gives the sensitivity of that. Vega and rho are the sensitivities with respect to volatility and interest rates. So these Greeks are very important, and especially when sell side makes markets, they need to know these sensitivities and they need to compute these to manage their risk. Let's now quickly look at the option pricing models. We'll not go into detail, this is a very complex topic. The main idea here is we want to model the asset prices as stochastic processes in continuous time. So you need to have some knowledge of stochastic calculus to model this, the dynamics of these asset prices. So here I'm showing the SDE or the stochastic differential equation for Black-Scholes. Black-Scholes is just dependent on the volatility, and W is the Brownian motion. And if you take, if you assume, obviously the volatility is not constant, you can also model the dynamics of the variance process. Then you have stochastic volatility models, where we have two correlated Brownian motions, one for the underlying asset and one for the variance process. So here I'm showing you the SDE of Heston. So from these SDEs, we can use Ito's lemma to compute to get the PDEs for pricing the options. These PDEs, in the case of Black-Scholes, have one time and one space variable, but in the case of Heston, for example, or stochastic volatility models, we need two space and one time variable. And then we have the initial conditions, we apply the boundary conditions, and we just solve the PDEs using finite differences. We can also use Monte Carlo, but Monte Carlo tends to be much slower than PDEs. I'm just showing you here the Black-Scholes and the Heston PDEs. As you can see, in the case of Black-Scholes, you have one time variable and one space variable. And Heston has two space variables and one time variable. So you need to know the derivatives with respect to both the variables and the cross derivatives. So it's much more complicated to solve this PDE. So here I'm showing you the diagram where price of the option at maturity is just the intrinsic value, which is the one in pink, and the green is the nonlinear price before the maturity. And again, Greeks are also like nonlinear, and you can see how the Greeks look like. That sensitivities of the option. Like if you take the derivative of the option, you get the Greeks here, and this is the vega here. Let's now look at how machine learning techniques can be applied for pricing options. So the idea here is we start with the slow numerical prices, which I had shown before, like PDEs or Monte Carlo, and then we generate millions and millions of training samples. Training samples means all the input features and the label, which is the price of the option. And once we have this training data set, we train deep learning, like deep neural networks, to learn the pricing function. Because we have seen the price is a smooth nonlinear function of all these inputs. So we can train a neural network to learn the prices. And once you train the model, you can do it all offline. We can use the trained model for inference, and that's just a forward pass in the neural network. The pricing is much faster. We can just do it in batches. So that's the key idea here. And not only the prices, we can also recover the Greeks, because they are the derivatives of the output with respect to all the inputs. And using the autograd of these neural networks, we can easily compute the Greeks as well. So to generate the training samples, we have to generate a lot of training samples because there are at least 6 to 8 inputs here. And to get a representative sample, we need to take a range of each of the inputs. And then we use what is called a Latin hypercube sampling. So what we do here is we want to make sure that in at least one point is simulated within each cell. So that's the idea of Latin hypercube sampling. This diagram shows that. If you do random sampling, we get something like this. But if you do like a Latin hypercube, we make sure that all the cells are represented in the data set. Black-Scholes European is an excellent base case because we can compute the price in closed form. It's just a simple formula. And using that formula, we can generate millions of samples. And it just takes a few milliseconds to generate millions of samples using this closed form. And the nice thing is it can be completely vectorized. And it forms an excellent base case for American option pricing. For American options, unfortunately, there is no closed form solution, so we need to solve a PDE. And this PDE, unfortunately, cannot be vectorized. So we have to solve it sample by sample. And here I'm just showing you some code and the time it takes to price these options. For American options, one sample is taking like 5 milliseconds on my laptop, whereas all the 3 million samples can be just done in 200 milliseconds per European. So you can see how slow American option pricing is. And if you extend to stochastic volatility models, it becomes order of magnitude slower because we have to solve what is called a 2D PDE or maybe 3D PDEs if you take into account the FX rates as well. And again, these pricing cannot be vectorized. So you have to do sample by sample. So for Heston, it's almost taking like 3 seconds on my laptop. So you can imagine how slow it is to generate millions of samples, right? And that's where the deep learning methods can be very helpful. We can just take our time to build this training data set, and then you can train the deep learning models. I'm just showing you a 3D surface of the American put priced in Heston model. As you can see, the European and American nice, smooth, nonlinear functions of inputs. So that's where we can hope that the deep learning model will learn this smooth, nonlinear function. We also have to be careful about special situations when we generate the training data. The option price becomes singular in situations where the time to maturity is 0 or when the volatility becomes 0. It's no longer a smooth, it becomes a piecewise linear, right? So if the deep learning model is not aware of these scenarios, it just sees points here and points here, it's just going to do an extrapolation. It doesn't know that there is a point right here at the singularity. So it's important to pay special attention to these kind of scenarios and generate a lot of training samples, especially in these areas of singularity. Now comes, so far I've talked about how to generate the training data. Now let's look at how to build a network architecture and train the neural networks. So for the network architecture, we need to select how many hidden layers and how many neurons per layer. All these are hyperparameters. And what kind of activation functions we need to use. Should we use ReLU or CellU or SoftPlus? There are a lot of choices here. And how do you prepare the data set for the deep learning model? And finally, how do we train these models on using GPUs? To make the hyperparameter choices easy, we just went with a flat neural network. By flat, I mean all the hidden layers have the same number of neurons. That way, we don't have to worry about the number of neurons per each layer. So in my training, I think I took like 4 hidden layers with 128 neurons per layer. Now let's look at activation functions. The classical activation function is ReLU. That's what is used in most of the deep learning models. But we'll see why ReLU is a bad choice. And we have smooth activation functions like SoftPlus or CellU. We ideally want to take activation functions which have smooth second derivatives, because we are not only trying to learn the prices, we are also trying to learn the Greeks. And that's where having a smooth activation function is very important. So let me show you a demo of these are all some Jupyter notebooks. I'm just running some nice visualizations. So here we have ReLU, which is piecewise linear. It's not smooth. So if you take the first derivative and the second derivative, there is a discontinuity at 0, right? And the second derivative is just a Dirac at 0, it goes to infinity. So ReLU is unfortunately not a good choice for an activation function, especially when you're trying to learn the grades. Soft plus is very smooth. It has the smooth first and second order derivatives, so soft plus is an excellent choice. CELU is not bad, it's smooth. And if you take CELU, again, it has two components, a nonlinear and a linear component, and there is a discontinuity at 0. So CELU is again not a good choice for an activation function. So it's very important to understand why these activation functions, like we can't just randomly put them in a grid search and do some cross-validation. It's important to understand how they work. And for our specific use case, ReLU and CELU are not good choices. And now we have to start the training process. So we do the usual stuff. We need to scale the features because the scale of each feature is totally different. So it's important to scale the features so using the standard scaling, for example. And it's also important how to use the scalar during inference. You need to use the scalar properly when learning prices and leads. So it's important to understand how to do that. So the training process is we need to choose how many epochs to run the training process, what is the path size, what kind of optimizer to use, and all these are hyperparameters. So we try with different learning rates, and then we pick the model which gives the best out of sample error, which minimizes the out of sample error. It's also important to have a learning rate decay. As you can see in this diagram, the loss goes down, but if you notice, wherever there is a decay in the learning rate, the loss drops down drastically. So it's important to use learning rate decay. At Bloomberg, we have a data science platform where we can specify the jobs using YAML specs. We can run some notebooks, or we can do some compute jobs. Or we also have what is called a hypertune job, where I can run like 20 jobs in parallel using 20 GPUs simultaneously. So we can try different combinations of hyperparameters and run them parallelly and have all the results in a couple of hours. We also use extensively S3 buckets for storing all our results and models and everything. Yeah, as I was mentioning, the hypertune job lets us do parallel execution using 1 GPU per job. We also want to collect a lot of instrumentation when the training is happening, like what are the training and loss validation losses for each epoch, and how does the learning rate decay schedule looks like, so that after the training process, if you have to debug something, we have all the data and we can have some nice tools to visualize all these results. And we also persist not only the model, the trained model, we also persist all the stats like R square, and all the predictions, so that we have all the results once the training is done. So here I'm showing you the statistics for Black-Scholes European, which is a base case. You don't need a machine learning model to price in Black-Scholes European. But as you can see that the machine is learning really well for this choice of activation and learning rate, soft plus and I think 1 × -3. And similarly for the American options, I think that's where the deep learning models really shine, because the numerical methods are super slow for American options. Again, we get very good accuracy of both prices and Greeks in the American options. So I was mentioning before how the deep learning model can learn the Greeks as well. So what are Greeks? Greeks are the partial derivatives of the output y with respect to all the inputs, right? So when you do the forward pass, we store all the derivatives, partial derivatives, because they are used for propagating the gradients, and in the back propagation, we use those gradients to update the weights. The nice thing about, so in PyTorch, it's literally like 4 lines of code where you can get all these grads, all the gradient vectors in just one shot. So let me show you one more quick demo. Yeah. So here we have a nice tool called introspection. What it does is it gives you, think of it as a partial dependency plot, where if you have a smooth function of multiple inputs and one output, you can freeze one of the inputs. For example, here I'm freezing all the other inputs and letting only the S vary along the x-axis. Right? So this is a nice way to look at how the function looks when we change different inputs. For example, now it's making it as a function of R, that I'm making R vary along the x-axis and freezing all these other inputs to these values, so I can change the inputs. But this is a nice way to quickly look at how the multivariate function looks like. And not only this, this is a true value. We can overlay the machine, the deep learning model values also directly on top of this. So let's now look at some of the machine learning models we talked about. Let's pick soft plus here. And now I'm comparing the true price versus the machine learning model price. As you can see, they're pretty close. I mean, they're almost on top of each other, so you can't even see the difference. But you can also look at how the Greeks evolved. You can see some differences in the Greeks, as you can see, because we didn't explicitly use the Greeks in the training process, right? The Greeks were as a side effect of the learning process. We only gave the prices as the training samples. The machine knows nothing about partial derivatives or anything. But it's amazing that it learned these prices, the Greeks really well. And so this is the area of singularity I was talking about. When the Greeks and the price become singular, you see that there are still some issues because we haven't added that many samples along the area of singularity. Let's see how the ReLU model did. So I'm going to overlay ReLU on top of this. So ReLU did a good job when it's trying to learn the price, but for Greeks, unfortunately, it's horrible, as I was mentioning before, because ReLU has some issues with the derivatives, right? The first and second derivatives of ReLU are singular. So as you can see, the Greeks ReLU model did not do a good job. Here I'm also showing you vega. So ReLU is a bad choice, as you can see from here. These kind of tools are an excellent way of quickly understanding how the model works and how we can compare the model predicted prices with the true prices, or the ground truth. We're also looking at techniques like differential learning, where we also incorporate the Greeks into the training process. So previously we were just using the prices, and we're trying to learn Greeks as a side effect. But actually we can do, we can also use Greeks inside the training process. So the training samples will contain the prices and the Greeks. And now the labels include prices in Greeks. The Greeks are the gradients. And in the loss function, you also use the Greeks for computing the loss. And that way, we can simultaneously learn the prices in Greeks. This is still in research phase. We haven't had solid results, but this is something we can look at. So that's all I have. Hopefully, be able to gain some understanding of how fast pricing using algorithms.